Welcome to this ultimate deep dive into time series forecasting in TimeGPT. From the basics of trends and seasonality to the latest breakthroughs with foundation models like TimeGPT, we'll cover 200 expert-level interview questions and answers. Whether you're preparing for a data science interview, building production-ready forecasting systems, or just passionate about the future of AI, this is your one-stop guide. Stay tuned till the end. This could be the only video you'll ever need on time series forecasting. What is time series data? Time series data is a sequence of observations collected over time, usually at equal intervals, like daily stock prices, hourly temperature, or monthly sales. Unlike regular datasets, time series has an inherent temporal order, meaning past values influence future values. This dependency makes forecasting unique compared to standard regression problems. What are the key components of a time series? A time series typically has four components: trend, long-term direction; seasonality, repeating patterns like monthly sales peaks; cyclic variations, irregular, long-term cycles like business cycles; and residual or noise, random fluctuations. Identifying these components helps select the right forecasting model. What is the difference between stationary and non-stationary series? A stationary series has constant mean, variance, and autocorrelation over time, making it easier to model. Non-stationary series show trends, seasonality, or changing variance. Many forecasting models, like ARIMA, assume stationarity, so data transformations like differencing or detrending are applied to stabilize it. What is autocorrelation in time series? Autocorrelation measures how related a variable is to its past values. For example, today's temperature may be correlated with yesterday's. The autocorrelation function, ACF, shows correlations at different lags, helping identify patterns like seasonality or lag effects for model selection. What is partial autocorrelation? Partial autocorrelation measures the direct relationship between a time series and its lag, controlling for intermediate lags. For example, PACF at lag 2 shows correlation with 2 steps back, excluding influence from lag 1. PAC plots are used to identify AR autoregressive order in ARIMA models. What is white noise in time series? White noise is a series of random values with zero mean, constant variance, and no autocorrelation. If residuals of a model resemble white noise, it means the model has captured all systematic patterns. Otherwise, remaining structure indicates underfitting. What is a random walk? A random walk is a non-stationary time series where each value depends on the previous one plus random noise. For example, YT equals YT minus 1 plus epsilon t. Stock prices often approximate random walks, making them difficult to predict. Differencing usually transforms random walks into stationary series. What is lag in time series? Lag refers to how far back in time you look. For instance, lag 1 means yesterday's value. Lag 7 means a week ago. Lag features capture dependencies over time and are essential in models like ARIMA or regression-based forecasting. What is seasonality in time series? Seasonality is a repeating pattern at fixed intervals: daily, weekly, monthly, or yearly. For example, electricity demand spikes daily in the evenings, or retail sales rise every December. Detecting seasonality ensures the model captures these recurring effects. What is trend in time series? Trend represents the long-term direction of data, either upward, downward, or flat. For instance, global CO2 levels show an upward trend over decades. Capturing trend is vital because ignoring it can lead to underestimation or overestimation in forecasts. What is cyclic behavior in time series? Cycles are irregular, long-term patterns not tied to a fixed calendar. For example, economic booms and recessions may span years. Unlike seasonality, cycles don't have a fixed frequency, making them harder to model. What is the difference between univariate and multivariate time series? Univariate time series has one variable observed over time, like daily sales. Multivariate includes multiple variables evolving together, like sales, marketing spend, and holidays. Multivariate forecasting can capture dependencies between variables, improving accuracy. What is decomposition in time series? Decomposition splits a series into components: trend, seasonality, and residuals. This helps understand underlying patterns and choose the right model. Decomposition can be additive when effects add up, or multiplicative when effects multiply, like seasonal percentage changes. What is differencing in time series? Differencing transforms a non-stationary series into stationary by subtracting consecutive values. For example, yt minus yt minus 1. It removes trends and stabilizes mean, making data suitable for ARIMA models. Higher-order differencing may be needed if one step isn't enough. What is the Box-Jenkins methodology? The Box-Jenkins method is a systematic approach to building ARIMA models. Steps include identifying the model using ACF or PACF, estimating parameters, checking residuals, and iterating. It ensures the model captures structure while residuals resemble white noise. What are exogenous variables in time series? Exogenous variables X are external factors that influence the series, like weather affecting electricity demand or promotions affecting sales. Models like ARIMAX or SARIMAX incorporate these variables, improving forecasts by capturing external drivers. What is the difference between forecasting and prediction? Prediction is a broad term for estimating unknown outcomes. Forecasting specifically refers to predicting future values based on past time series data. In time series, forecasting is usually quantitative, while prediction can also include classification or other tasks. What is the difference between short-term and long-term forecasting? Short-term forecasting predicts the immediate future, example is next few hours or days, useful for operations. Long-term forecasting spans weeks, months, or years, guiding strategy. Short-term models often rely on recent patterns, while long-term forecasts need to capture trend and seasonality. What is backtesting in time series forecasting? Backtesting evaluates a forecasting model by simulating predictions on historical data. You split data into training and test sets. Example is walk-forward validation. Train on past values and compare predictions against actuals. It measures how well the model generalizes to unseen data. What are some challenges unique to time series forecasting? Challenges include non-stationarity, seasonality, noise, missing values, and concept drift over time. Unlike standard ML problems, temporal dependencies and order matter, so you can't shuffle data randomly. Choosing proper validation, handling exogenous factors, and balancing short versus long-term accuracy are key difficulties. What is AR in time series forecasting? AR stands for Autoregressive Model. It predicts the current value based on a linear combination of its past values. For example, AR1 means the current value depends on the immediately previous value plus noise. The order P in ARP indicates how many lags are included. It's effective when past values strongly influence the present. What is MA in time series forecasting? MA stands for Moving Average Model. Unlike AR, it predicts the current value based on past forecast errors. For example, MA1 uses the last residual to adjust the forecast. The order Q determines how many past error terms are considered. MA models capture short-term noise patterns in a series. What is ARMA and when is it used? ARMA combines autoregressive AR and moving average MA components. It's suitable for stationary series that exhibit both lag relationships and noise dependence. The AR part models past values, while the MA part accounts for residual correlations. ARMA is a foundational model for short-term forecasting. What is ARIMA and how does it extend ARMA? ARIMA stands for Auto-Regressive Integrated Moving Average. It extends ARMA by adding the I component, integration, which means differencing the data to remove trends and make it stationary. ARIMA of PDQ is widely used for univariate forecasting when data shows trends but no strong seasonal patterns. What does the PDQ in ARIMA represent? P, order of autoregression, number of lag terms. D, degree of differencing, to remove trend. Q, order of moving average, number of lag forecast errors. For example, ARIMA of 2, 1, 1 means 2 AR terms, 1 differencing, and 1 MA term. What is SARIMA, and how does it differ from ARIMA? SARIMA, seasonal ARIMA, extends ARIMA by adding seasonal components. It models both non-seasonal and seasonal behavior using parameters P, D, Q, S, where S is the seasonal period. For example, monthly sales with yearly seasonality can be modeled using SARIMA. It's better suited for data with strong repeating seasonal patterns. What is SARIMAX and when is it useful? SARIMAX adds exogenous variables X to SARIMA. These are external factors like weather, holidays, or promotions that affect the series. SARIMAX is powerful when outside influences significantly drive the target series, as it combines trend, seasonality, and external effects. What is the Box-Jenkins methodology? The Box-Jenkins approach is a structured method for building ARIMA or SARIMA models. It involves 1. Identification using ACF-PASCF plots. 2. Estimation, fitting parameters. 3. Diagnostic checking, residual analysis. This iterative process ensures the final model is both statistically sound and accurate. What is exponential smoothing? Exponential smoothing forecasts by weighting past observations with recent values given more importance. Unlike ARIMA, it doesn't require stationarity. It's simple, fast, and effective for short-term forecasting. Variants include simple, double Holt's, and triple Holt-Winters exponential smoothing. What is Holt's linear trend method? Holt's method extends exponential smoothing to handle trends. It uses 2 components, one for the level and one for the trend, each updated with smoothing parameters. This allows forecasts that follow upward or downward trends, unlike simple smoothing, which assumes no trend. What is Holt-Winters method? Holt-Winters, or triple exponential smoothing, extends Holt's method by adding seasonality. It models level, trend, and seasonal components. 2 variants exist: additive for constant seasonal effects, and multiplicative for seasonality proportional to level. It's widely used in business forecasting like retail sales. What are the differences between ARIMA and Holt-Winters? ARIMA requires stationarity and models data using autoregression and moving averages. Holt-Winters doesn't require differencing and explicitly models level, trend, and seasonality with smoothing. ARIMA is more statistical and flexible, while Holt-Winters is more intuitive and often easier for business users. What is ETS in time series forecasting? ETS stands for Error, Trend, Seasonal Models, a generalization of exponential smoothing. It selects whether to include error, trend, and seasonal components as additive or multiplicative. The ETS framework provides a systematic way to choose the best smoothing method. What are unit root tests and why are they used? Unit root tests, like the Augmented Dickey-Fuller, ADF, or KPSS test, check if a time series is stationary. A unit root indicates non-stationarity, often requiring differencing. These tests guide whether ARIMA can be applied directly or transformations are needed. How do you identify ARIMA parameters of P, D, Q? P suggested by PAC plots. D determined by unit root tests or by differencing until stationarity. Q suggested by ACF plots. Experimentation, information criteria, AIC or BIC, and validation help finalize parameters. What are AIC and BIC in model selection? AIC, a Keiki information criterion, and BIC, Bayesian information criterion, measure model fit while penalizing complexity. Lower AIC or BIC values indicate better models. They're commonly used to compare ARIMA or SARIMA models with different orders. What is profit and how does it compare to ARIMA? Profit, developed by Facebook, is a model for time series with trend and seasonality. Unlike ARIMA, it's highly automated, robust to missing data, and handles holiday effects well. While less statistical, Profit is popular in business settings for quick, interpretable forecasting. What are the limitations of ARIMA models? ARIMA struggles with complex nonlinear relationships, requires stationarity, and doesn't handle multiple exogenous variables naturally. It can also be computationally expensive for large datasets. In practice, ARIMA may underperform against ML or DL methods when patterns are nonlinear or high-dimensional. When should you prefer Holt-Winters over ARIMA? Holt-Winters is preferred when seasonality and trends are strong and interpretable, and when a quick, explainable solution is needed. ARIMA is better for data requiring more flexibility or where rigorous statistical validation is required. Holt-Winters is more business-friendly, ARIMA more statistically grounded. Why are classical forecasting methods still relevant today? Despite deep learning advances, classical methods remain powerful for small datasets, short-term forecasts, and interpretable results. They're fast, require fewer resources, and often outperform complex models in business contexts. They also serve as strong baselines when evaluating advanced approaches. Why is pre-processing important in time series forecasting? Pre-processing ensures that data is clean, consistent, and ready for modeling. Time series often have missing values, outliers, or non-stationarity. Without pre-processing, models may misinterpret patterns, leading to poor forecasts. Good pre-processing improves accuracy, stability, and interpretability. How do you handle missing values in time series? Options include forward fill, backward fill, linear interpolation, spline methods, or model-based imputation. The choice depends on context. For sensor data, forward fill may work, but for financial data, interpolation is often safer. Consistent handling avoids biasing the model. How do you detect and handle outliers in time series? Outliers can be detected using statistical methods, z-scores, IQR, rolling averages, or model-based residual analysis. Handling options include removal, Windsorization, or replacing with smooth values. In forecasting, extreme events may be valid signals, so domain knowledge is crucial before removing them. What is scaling, and why is it needed in time series? Scaling transforms values to a consistent range. For ML or DL models, standardization, z-score, or normalization, min-max, ensures stable training. For example, LSTMs converge faster with normalized inputs. Scaling is less critical for ARIMA but essential for gradient-based models. What are lag features in time series forecasting? Lag features use past values as predictors. For example, predicting sales today using sales from 7 days ago, lag 7. They help ML models like regression or XGBoost capture temporal dependencies that classical models handle inherently. What are rolling statistics and how are they used? Rolling statistics compute metrics like mean, variance, or max over a sliding window. Example is 7-day moving average. They capture short-term trends and seasonality effects. Rolling features are often used in ML pipelines for richer temporal information. What is differencing and why is it applied? Differencing removes trends and stabilizes mean, making series stationary. For example, y sub t minus y sub t minus 1 removes linear trends. Seasonal differencing, y sub t minus y sub t minus s, handles recurring seasonal patterns. It's often a pre-processing step for ARIMA-type models. What is seasonal decomposition in time series? Seasonal decomposition splits a series into trend, seasonality, and residuals. Additive models assume components add up, while multiplicative assumes interactions. Decomposition helps detect structure, identify anomalies, and guide model choice. How do Fourier terms help in modeling seasonality? Fourier terms approximate seasonal patterns using sine and cosine functions. They're especially useful for complex or multiple seasonalities, such as daily and yearly effects in energy data. They're often added as exogenous features in regression or ML models. What is the difference between additive and multiplicative decomposition? Additive, observed equals trend plus seasonality plus residuals, when seasonality is constant. Multiplicative, observed equals trend times seasonality times residuals, when seasonal effects grow/shrink with level. Choosing the right type avoids bias in decomposition. What is feature extraction from timestamps? Timestamps can generate features like hour, day of week, month, or holidays. For example, sales may spike on weekends or during December. These engineered features give ML or DL models extra context beyond raw series values. How do you handle multiple seasonalities in time series? Standard models like ARIMA struggle with multiple seasonalities. Approaches include TBATS, Fourier terms, profit, or neural networks with seasonal embeddings. For example, ride-hailing demand shows daily and weekly cycles, requiring models that handle both. What is windowing and time series forecasting? Windowing converts sequential data into supervised learning form. For example, using the past 10 days' values as features to predict the next day. It's essential for ML or DL models like XGBoost or LSTMs that require tabular input. How do you handle non-stationarity in time series? Techniques include differencing, detrending, seasonal adjustment, or applying transformations like log, Box-Cox, or Yo-Johnson. Ensuring stationarity is crucial for models like ARIMA, while ML or DL models can sometimes handle non-stationarity directly. How do you handle categorical events in time series? Categorical events like holidays or promotions can be encoded as binary flags or dummy variables. These exogenous features often explain demand spikes or drops, improving forecast accuracy when combined with statistical or ML models. How do you smooth time series data? Smoothing removes noise to reveal patterns. Methods include moving averages, exponential smoothing, or low-S. While smoothing can help visualization and feature creation, over-smoothing risks hiding true signals. What are anomalies in time series and how are they treated? Anomalies are unexpected spikes or drops outside normal patterns. They can be identified with decomposition residuals, statistical thresholds, or ML methods. Depending on context, anomalies may be corrected, flagged, or modeled separately. How do you split time series for training and testing? Unlike random splits, time series must preserve temporal order. Common strategies include holdout, train on past, test on future, or rolling window, walk-forward validation. This ensures realistic evaluation of forecasting performance. What is backshift transformation in time series? Backshifting moves a series backward by one or more periods to create lag features. For example, shifting sales data by 1 day creates a lag 1 feature. It's a core technique in feature engineering for supervised learning models. How do you deal with heteroscedasticity in time series? Heteroscedasticity means changing variance over time. Solutions include log transformation, Box-Cox transformation, or using models designed for variance shifts, like GARCH. Addressing it stabilizes variance and improves model reliability. How is linear regression used for time series forecasting? Linear regression can be applied by transforming time series into a supervised problem. Lag values, rolling statistics, or external variables become predictors, and the target is the next time step. It's simple, interpretable, and effective for short-term dependencies, though it struggles with complex seasonality. What is the main challenge of applying standard ML models to time series? The main challenge is that ML models assume independent and identically distributed RIID data, but time series has temporal dependence. You must engineer lag features, rolling windows, or differences to expose temporal patterns. Without this pre-processing, ML models may misinterpret sequences. How do decision trees handle time series forecasting? Decision trees split data based on features like lags, rolling averages, or calendar variables. They capture nonlinear relationships and interactions well. However, single trees are prone to overfitting and typically underperform ensembles in forecasting tasks. What role do random forests play in time series forecasting? Random forests combine multiple decision trees trained on bootstrap samples with feature randomness. They handle nonlinearities, noise, and interactions better than single trees. They're robust but don't naturally extrapolate trends or seasonality, so feature engineering is critical. How does gradient boosting, XGBoost, light GBM, cat boost, apply to time series? Boosting methods iteratively build trees that correct errors of prior ones. With engineered features, lags, rolling stats, Fourier terms, they achieve strong forecasting accuracy. They often outperform classical models, especially with large data sets and exogenous variables, but can be computationally heavier. How is feature importance used in tree-based models for time series? Feature importance scores from random forests or XGBoost highlight which lags, rolling stats, or external variables most influence forecasts. This provides interpretability and helps refine feature engineering. For example, knowing that lag 7 is critical suggests weekly seasonality. What is walk-forward validation in ML for time series? Walk-forward validation trains a model on initial data, tests on the next window, then rolls forward, repeating the process. This mimics real-world forecasting, where future data is never available at training time. It's more reliable than random splits for evaluating time series models. How do you incorporate seasonality into ML models? Seasonality can be captured through engineered features, Fourier terms, dummy variables for months or weekdays, or lag seasonal values. Example is lag 12 for yearly monthly data. These features help ML models learn repeating patterns similar to what SARIMA models capture. What is multi-step forecasting, and how do ML models handle it? Multi-step forecasting predicts several future time points. Strategies include recursive forecasting, predict one step ahead, then feedback predictions. Direct forecasting, train separate models for each. Horizon or sequence-to-sequence models. Direct methods reduce error accumulation but require more computation. How do ML models handle multivariate time series? In multivariate forecasting, ML models use lagged features from multiple related series as predictors. For example, sales may depend on both price and marketing spend. Models like XGBoost or random forests can naturally handle many variables, capturing cross-dependencies. How do you prevent data leakage in time series ML? Data leakage occurs when future information leaks into training. To prevent it, split data chronologically, avoid using future lags, and carefully design rolling statistics so they only use past values. Proper walk-forward validation also ensures no future information contaminates training. How can clustering be used in time series forecasting? Clustering groups similar time series or segments within a series. For example, grouping stores with similar demand patterns allows building shared models. Techniques like k-means on extracted features, trend, seasonality, help scale forecasting to large numbers of series. How can dimensionality reduction help in time series forecasting? Techniques like PCA or autoencoders reduce large sets of lag features or multivariate series into compact representations. This simplifies models, reduces noise, and can improve forecasting performance by highlighting key latent patterns. What is the difference between direct and recursive forecasting with ML? Recursive. Train one model for one-step forecasts, then repeatedly feed predictions forward. Simple but error accumulates. Direct. Train separate models for each horizon, one-step, two-step. More accurate but computationally heavier. Hybrid strategies combine both. How can ML handle irregularly spaced time series? ML models typically expect fixed intervals. For irregular series, you can resample data, interpolate missing points, or engineer features like time since last event. Alternatively, survival models or specialized temporal ML methods can handle irregularities directly. What role do external, exogenous variables play in ML forecasting? Exogenous features like weather, holidays, or marketing often explain major variations. Tree-based models naturally integrate them, while regression and boosting rely on engineered external features. Properly incorporating exogenous factors significantly boosts forecast accuracy. How can ensembles improve machine learning time series forecasting? Ensembles combine multiple models. Examples are random forest, XGBoost, linear regression to balance strengths. Weighted or stacked ensembles often outperform single models by reducing variance and bias. For example, blending ARIMA with XGBoost can capture both linear and nonlinear patterns. How do anomaly detection techniques integrate with ML forecasting? ML models can incorporate anomaly flags as features or be trained with robust loss functions. Forecast residuals can also signal anomalies. Integrating anomaly detection ensures models don't overfit to rare events and can alert when forecasts deviate unexpectedly. How do you evaluate ML-based time series models? Use walk-forward validation with metrics like RMSE, MAE, or MAPE. Compare against baselines like naive forecasts or ARIMA. Evaluation should also consider stability across multiple horizons, robustness to shocks, and business relevance of errors. What are the main advantages and disadvantages of ML over classical methods in time series? Advantages: handles large data sets, nonlinearities, and exogenous features well. Scales better in multivariate contexts. Disadvantages: requires heavy feature engineering, less interpretable, and prone to overfitting. Classical methods remain competitive for simple, short series or when interpretability is critical. Why use deep learning for time series forecasting? Deep learning excels at capturing nonlinear, long-range dependencies in complex datasets. While ARIMA and ML rely heavily on feature engineering, neural networks can automatically learn representations, handling multivariate, high-dimensional, and irregular time series. They also scale well for large datasets. What are recurrent neural networks, RNNs, in time series forecasting? RNNs process sequences step by step, maintaining a hidden state that carries past information forward. This makes them suitable for time series. However, vanilla RNNs suffer from vanishing/exploding gradients, making them ineffective for long sequences. How do long short-term memory LSTM networks improve over RNNs? LSTMs introduce gates, input, forget, output, to control information flow. This allows them to remember long-term dependencies and avoid vanishing gradients. LSTMs are widely used in forecasting tasks like energy load or traffic predictions. What is a gated recurrent unit, and how does it differ from LSTM? GRUs are a simplified version of LSTMs with two gates, reset and update. They train faster, use fewer parameters, and often perform comparably to LSTMs. GRUs are preferred when computational efficiency matters. What are the drawbacks of LSTMs in forecasting? They require large datasets, are computationally expensive, and don't parallelize well due to sequential processing. They also struggle with very long-term dependencies compared to attention-based models like transformers. What are bidirectional RNNs in time series? Bidirectional RNNs process sequences both forward and backward, capturing dependencies from past and future. While powerful, they're not always suitable for forecasting since future data isn't available, but they work well for sequence classification or anomaly detection. How do sequence-to-sequence models apply to forecasting? Sequence-to-sequence models use an encoder to process past data and a decoder to predict multiple future steps. They're ideal for multi-step forecasting. For example, predicting the next 24 hours of energy demand using the past week's history. What are temporal convolutional networks, TCNs? TCNs use 1D dilated causal convolutions to capture long-range dependencies in parallel, unlike RNNs. They're efficient, stable to train, and often outperform RNNs for time series. TCNs are widely used in industry for scalable forecasting. How do CNNs apply to time series forecasting? CNNs extract local patterns from windows of time series, similar to image processing. They're effective for short-term dependencies and multivariate forecasting. Combined with pooling, CNNs can reduce noise and highlight key trends. What are attention mechanisms in forecasting? Attention assigns different weights to past time steps based on relevance. Instead of relying only on nearby lags, models can focus on specific important time points. Attention mechanisms underpin modern transformer models for time series. What is the transformer architecture, and why is it important for time series? Transformers replace recurrence with self-attention, allowing models to capture long-term dependencies in parallel. They scale well, handle multivariate data, and achieve state-of-the-art results in time series forecasting, anomaly detection, and classification. How do transformers handle seasonality and trend in time series? Transformers capture seasonality through attention weights and positional encodings. Extensions like Informer, Autoformer, and FED-Former add decomposition or autocorrelation mechanisms specifically tailored to time series, seasonality, and trend. What is the Informer model? Informer is a transformer-based model optimized for long sequence forecasting. It uses prob-sparse self-attention to reduce complexity and a generative-style decoder. This makes it efficient for long-horizon forecasting with large datasets. What is the Autoformer model? Autoformer extends transformers by introducing seasonal trend decomposition within the architecture. It explicitly separates trend and seasonal components, improving accuracy for long-term forecasting where classical transformers may drift. What is the FED-former model? FED-former, frequency-enhanced decomposed transformer, applies Fourier transforms to capture global seasonal patterns efficiently. It combines frequency domain analysis with attention, making it powerful for datasets with strong periodicities like climate or energy. How do hybrid models combine deep learning with classical methods? Hybrid models integrate statistical decomposition with neural networks. For example, trend and seasonality may be modeled with Holt-Winters, while LSTMs capture residual patterns. This leverages the strengths of both approaches for robust forecasting. How does DeepAR work? DeepAR, developed by Amazon, is an RNN-based probabilistic forecasting model. It predicts probability distributions of future values rather than single points, handling uncertainty well. It's particularly useful for demand forecasting across many related series. How does NBEATS work? NBEATS is a neural basis expansion model that directly learns trend and seasonality through fully connected networks. It avoids explicit statistical assumptions and has shown strong performance across benchmark datasets, sometimes outperforming LSTMs and transformers. What is the role of embeddings in time series deep learning? Embeddings convert categorical variables like day of week or location into dense vectors, allowing models to learn relationships more effectively. This is crucial for multivariate and hierarchical forecasting where categorical context matters. How do you train deep learning models for time series forecasting? Steps include preparing lagged windowed datasets, scaling features, splitting chronologically, and defining horizons. Models are trained with losses like mean squared error, mean absolute error, or pinball loss for quantiles. Early stopping, dropout, and proper validation prevent overfitting. How do you handle multi-step forecasting with deep learning? Strategies include recursive, feed predictions forward, direct, train separate models per horizon, sequence 2, sequence or transformers, predict all steps at once. Sequence 2, sequence and transformers are preferred for long horizons due to reduced error accumulation. What are probabilistic forecasting models in deep learning? Models like DeepAR, temporal fusion transformers, or quantile regression LSTMs output distributions rather than point estimates. They provide prediction intervals, central in fields like finance or energy, where uncertainty matters as much as the forecast. How does the temporal fusion transformer TFT work? TFT combines LSTMs, attention, and gating mechanisms to capture both short-term and long-term patterns. It handles static covariates, dynamic variables, and provides interpretability through attention scores. TFT is widely applied in forecasting competitions. What are dilated convolutions and why are they useful in time series? Dilated convolutions skip inputs at defined intervals, expanding the receptive field without increasing kernel size. They allow TCNs to model long sequences efficiently while keeping computations parallelizable. What are the challenges of using deep learning in time series forecasting? Challenges include data hunger, large datasets needed, risk of overfitting, long training times, and interpretability. Unlike ARIMA, neural networks act as black boxes, requiring explainability techniques like SHAP or attention weights. How do you evaluate deep learning models for time series? Use walk-forward validation, backtesting, and metrics like RMSE, MAPE, or probabilistic scores. Compare against naive and classical baselines. Visualization of forecasts versus actuals is key to detect bias, drift, or underfitting. How does transfer learning apply in time series forecasting? Pre-trained models like TimeGPT or models trained on large corpora of series can be fine-tuned on new domains. Transfer learning improves accuracy in low data regimes, leveraging cross-domain temporal knowledge. How does data augmentation help in time series forecasting? Techniques include time warping, random sampling, noise injection, or bootstrapping subsequences. Augmentation increases data diversity, reduces overfitting, and helps deep learning models generalize better to unseen scenarios. How do you integrate exogenous variables in deep learning models? Exogenous variables can be added as additional input channels in CNNs or TCNs, or concatenated with lag features in RNNs or LSTMs. Transformers and TFT explicitly handle multiple covariates through embeddings and attention. How do you choose between LSTMs, TCNs, and transformers for forecasting? Use LSTMs or GRUs for moderate sequence lengths, smaller datasets. Use TCNs when parallelism and stability matter. Use transformers for long sequences, multivariate data, and large-scale tasks. The choice depends on data size, complexity, and computational resources. What is multivariate time series forecasting? Multivariate forecasting predicts a target variable using multiple related series. For example, forecasting sales using past sales, marketing spend, and economic indicators. It captures cross-variable dependencies and often improves accuracy over univariate models. How does multivariate forecasting differ from univariate forecasting? Univariate forecasting uses only past values of one series. Multivariate adds external variables that influence the target. While univariate is simpler, multivariate provides richer context but requires more data and careful feature engineering to avoid overfitting. What is probabilistic forecasting and why is it important? Probabilistic forecasting outputs a distribution of future values rather than a single point. It quantifies uncertainty, which is critical in finance, energy, and healthcare. For example, predicting demand with a 90% confidence interval helps manage risk better than a single estimate. What metrics are used to evaluate probabilistic forecasts? Metrics include pinball loss for quantiles, continuous ranked probability scores CRPS, and calibration measures like coverage probability. These evaluate how well-predicted distributions capture actual variability beyond point accuracy. What is quantile forecasting? Quantile forecasting predicts values at specific percentiles. Example are 10th, 50th, 90th. This provides prediction intervals instead of single values. Models like quantile regression, or DeepAR, use pinball loss to directly optimize for quantiles. What is hierarchical time series forecasting? Hierarchical forecasting involves data structured at multiple levels. Examples are sales by store, region, and total. Forecasts must be consistent across levels. Store forecasts should sum to total. Special reconciliation methods ensure this coherence. How do you reconcile hierarchical forecasts? Methods include top-down, example are forecast total, split across units, bottom-up, example are forecast each unit, sum up, and middle-out, example is combine both. More advanced reconciliation uses optimization, example is min-t, to ensure forecasts are statistically coherent. What is grouped time series forecasting? Grouped forecasting handles series that can be aggregated in multiple ways. Examples are by product, region, or both. Unlike strict hierarchies, groupings may overlap. Methods extend hierarchical reconciliation to ensure forecasts remain consistent across different groupings. What is global forecasting in time series? Global forecasting builds one model across multiple series rather than one model per series. For example, a global LSTM trained on sales across all stores. This leverages cross-series patterns, improves generalization, and is especially useful with small individual datasets. What is local forecasting, and how does it compare to global forecasting? Local forecasting builds a separate model for each series. It's more tailored, but may underperform when data is limited. Global models share information across series, often outperforming local ones in large-scale forecasting tasks. What is online learning in time series forecasting? Online learning updates models incrementally as new data arrives, rather than retraining from scratch. This is crucial in streaming applications like sensor data, stock prices, or IoT devices, where patterns shift over time. How does concept drift affect time series forecasting? Concept drift occurs when the statistical properties of data change over time, invalidating past patterns. For example, consumer demand shifts after a market disruption. Drift requires adaptive models, online learning, or periodic retraining. What are strategies to handle concept drift? Strategies include sliding or expanding windows, online learning algorithms, drift detection methods like DDM, ADWIN, and ensembles that adapt to changing distributions. Regular model monitoring is essential for detecting drift early. What is regime switching in time series? Regime switching means time series behave differently in different periods, such as bull versus bear markets. Models like Markov switching models capture these hidden states, allowing forecasts to adapt based on the current regime. What is anomaly detection in time series forecasting? Anomalies are points that deviate significantly from expected patterns. Detecting them prevents models from being skewed. Techniques include statistical thresholds, decomposition residuals, isolation forests, or deep learning methods like autoencoders. How do you handle irregularly spaced time series data? Options include resampling to fixed intervals, interpolation, or using models designed for irregular data. Example are neural ODS, Gaussian processes. The approach depends on whether missing intervals carry meaningful signals or should be normalized away. What is probabilistic hierarchical forecasting? It combines probabilistic forecasts with hierarchical structures, ensuring both uncertainty quantification and coherent aggregation. For example, forecasting demand distributions for individual stores that sum consistently to regional totals. How do Bayesian methods apply to time series forecasting? Bayesian models estimate full posterior distributions of parameters and forecasts, naturally quantifying uncertainty. Methods include Bayesian ARIMA, Gaussian processes, and Bayesian neural networks. They are useful when uncertainty is as important as accuracy. What are Gaussian processes in time series forecasting? Gaussian processes, GPS, are non-parametric Bayesian models that define distributions over functions. They capture uncertainty well and handle irregular data, but scale poorly with large datasets, O of n cubed. Sparse approximations improve scalability. What is multi-horizon forecasting and why is it challenging? Multi-horizon forecasting predicts multiple future time steps. Challenges include error accumulation, changing uncertainty, and different drivers for short versus long horizons. Sequence 2. Sequence models, transformers, and probabilistic methods are often used to address these. Why are evaluation metrics important in time series forecasting? Metrics quantify how well forecasts match reality, guiding model selection and improvement. Since different metrics emphasize different aspects, error size, scale, or uncertainty, choosing the right metric ensures alignment with business goals. What is mean absolute error, MAE? MAE is the average of absolute differences between predicted and actual values. It's intuitive and less sensitive to outliers than squared errors. However, it treats all errors equally, regardless of magnitude. What is root mean squared error, RMSE? RMSE is the square root of the average squared differences between predictions and actuals. It penalizes larger errors more heavily than MAE. RMSE is useful when big mistakes are especially costly. What is mean absolute percentage error, MAPE? MAPE expresses error as a percentage. MAPE equals 100 and sum of absolute value of y minus y hat over y. It's scale independent and easy to interpret. However, it's problematic when actual values are close to zero. What is symmetric MAPE, SMAPE? SMAPE adjusts MAPE by dividing by the average of actual and predicted values, making it symmetric. It avoids extreme percentages when actuals are near zero. It's widely used in forecasting competitions. What is mean squared logarithmic error, or MSLE? MSLE measures squared errors on the log scale, emphasizing relative differences. It's useful when growth rates matter more than absolute differences, like in population or financial forecasting. What is weighted absolute percentage error, WAPE? WAPE is total absolute error divided by total actual values. It's like MAPE but weighted, making it more stable with skewed distributions. Businesses often use it as a practical KPI. What is mean forecast error, MFE, and what does it indicate? MFE is the average of forecast errors predicted minus actual. A positive MFE indicates overestimation, negative indicates underestimation. It reveals bias, unlike MAE or RMSE, which measure error magnitude only. What is coverage in probabilistic forecasting? Coverage measures how often actual values fall within prediction intervals. For example, a 95% interval should contain true values about 95% of the time. Poor coverage means intervals are too narrow, underconfident, or too wide, overconfident. What is pinball loss and where is it used? Pinball loss evaluates quantile forecasts. It penalizes under and over predictions differently based on the chosen quantile. It's the standard loss for training quantile regression models and probabilistic forecasting methods. What is the continuous ranked probability score, CRPS? CRPS compares the predicted cumulative distribution to the observed outcome. Lower CRPS means better forecasts. It generalizes MAE to probabilistic forecasts, rewarding both sharpness and calibration. How do you evaluate forecasts across multiple horizons? Use horizon-specific metrics, short versus long-term, and aggregate scores. For example, measure MAE for 1 day ahead versus 30-day ahead separately. Multi-horizon evaluation prevents models that perform well short-term but fail long-term. What is backtesting in time series? Backtesting simulates forecasts on historical data to evaluate performance. The model is trained on past windows and tested on future segments. It's essential for realistic assessment since time series cannot be randomly split. What is rolling window validation? Rolling window validation repeatedly shifts the training and test sets forward, retraining at each step. This mimics real forecasting conditions and provides a distribution of performance scores, improving reliability of evaluation. What is expanding window validation? Expanding window validation starts with a small training set and expands it over time, always testing on the next period. It reflects scenarios where more data continuously becomes available, useful in finance or production systems. How do you choose the right error metric for a business case? Choice depends on objectives. Use MAE for interpretability, RMSE if large errors are costly, MAPE or SMAPE for percentage errors across scales, CRPS or pinball loss for probabilistic forecasts. The best metric aligns with decision-making needs. Why is scale important in evaluating errors? Raw errors like MAE or RMSE depend on the scale of the series, making comparisons across datasets difficult. Scale-independent metrics like MAPE, SMAPE, or normalized RMSE allow fairer evaluation across multiple series. What is Thiel's U statistic? Thiel's U compares model forecasts to a naive baseline, example last observed value. A U less than 1 indicates the model outperforms the naive forecast, while U greater than 1 means the baseline is better. It's a practical way to assess added value. What is forecast bias and how is it measured? Forecast bias is systematic under or over prediction. It's measured by metrics like MFE or percentage bias, PBIAS. Identifying bias is crucial because even models with low errors can mislead if consistently skewed in one direction. Why is it important to compare against naive or benchmark models? Benchmarks like last value or seasonal naive provide simple reference points. A complex model should outperform these. If not, it's overkill. Benchmarks ensure transparency and prevent deploying unnecessarily complex solutions. How is time series forecasting used in finance? In finance, forecasting is applied to stock prices, volatility, interest rates, and risk management. For example, ARIMA models capture short-term returns, while LSTMs and transformers model nonlinear dependencies. Accurate forecasts inform trading, portfolio optimization, and credit risk assessment. How is time series forecasting applied in retail? Retailers use forecasting to predict demand, optimize inventory, and plan promotions. For example, Holt-Winters can capture seasonal spikes in holiday sales, while XGBoost or Profit handle promotions and holidays. Forecasts prevent stockouts, reduce costs, and boost customer satisfaction. How is forecasting used in supply chain management? Forecasting demand across warehouses and suppliers ensures smooth logistics. Hierarchical forecasting reconciles forecasts from product level up to regional totals. Accurate predictions minimize overstock, cut costs, and improve service levels across supply chains. How is forecasting applied in energy systems? In energy, forecasting is vital for load demand, renewable generation, and pricing. Short-term forecasts balance supply and demand in real time, while long-term forecasts guide infrastructure planning. Methods range from SARIMA for load curves to deep learning for solar/wind patterns. How does forecasting help in healthcare? Healthcare uses forecasting for patient admissions, disease outbreaks, and ICU demand. For example, during COVID-19, time series models projected case growth and hospital needs. Forecasts guide resource allocation and improve patient care readiness. How is time series forecasting applied in weather and climate? Forecasting temperature, rainfall, or extreme events relies on time series models with exogenous inputs. Seasonal decomposition, ARIMA, and modern DL models capture periodicities. Accurate weather forecasts help agriculture, disaster planning, and energy sectors. How is forecasting used in anomaly detection? Forecasts can serve as baselines. If actuals deviate beyond thresholds, anomalies are flagged. This is used in fraud detection, sensor monitoring, and cybersecurity. Deep learning models like autoencoders and probabilistic forecasts enhance anomaly detection. What role does forecasting play in transportation? Transportation systems use forecasting for traffic flow, ride-hailing demand, and public transport planning. Multivariate LSTMs, or transformers, predict demand peaks. Accurate forecasts reduce congestion, improve fleet allocation, and enhance customer experience. How does forecasting benefit telecommunications? Telcos forecast network traffic, bandwidth usage, and service demand. Predicting spikes avoids outages and improves customer satisfaction. For example, TCNs model usage patterns across millions of users in near real time. How is forecasting applied in agriculture? Farmers and agribusinesses forecast crop yields, market demand, and prices. Models incorporate weather, soil, and historical yield data. Accurate forecasts reduce waste, optimize planting, and support food security planning. How does forecasting help in manufacturing? Manufacturers use forecasting to predict machine failures, predictive maintenance, demand for raw materials, and production cycles. Time series models integrated with IoT sensors prevent costly downtime and optimize supply flows. How is time series forecasting used in marketing? Marketers forecast campaign impacts, customer churn, and engagement trends. Seasonal effects, promotions, and external variables like holidays are modeled. Forecasts guide budget allocation and help personalize customer outreach. How is forecasting applied in financial risk management? Banks use forecasting for default rates, credit risk, and liquidity needs. Probabilistic forecasting quantifies uncertainty, helping stress test financial systems. Models like GRUs predict volatility, crucial for hedging strategies. How is forecasting applied in smart cities? Smart cities forecast energy consumption, traffic flow, and air pollution. Time series models with IoT data optimize resources, reduce emissions, and improve citizen services. Forecasting is foundational to real-time decision-making in urban planning. How is forecasting applied in call centers? Forecasts predict call volume, staffing needs, and service demand. Short-term forecasts optimize daily workforce scheduling, while long-term forecasts support capacity planning. Even small improvements reduce wait times and boost customer satisfaction. How is forecasting applied in cryptocurrency markets? Crypto forecasting faces extreme volatility. LSTMs, transformers, and probabilistic models attempt to capture nonlinear dependencies. Though challenging, even modestly accurate forecasts help investors manage risk in trading strategies. How does forecasting support sustainability initiatives? Forecasting energy demand, emissions, or resource consumption helps plan greener strategies. For example, predicting renewable energy output supports grid stability and reduces reliance on fossil fuels, contributing to climate goals. How is forecasting used in fraud detection? Unusual patterns in financial transactions or network activity are flagged when they deviate from forecasted baselines. Forecasting combined with anomaly detection identifies fraud in banking, e-commerce, and cybersecurity contexts. What role does forecasting play in IoT and sensor networks? IoT sensors generate massive real-time time series. Forecasts predict device failures, traffic loads, or environmental changes. Models must be efficient and adaptive for edge deployment, ensuring low-latency predictions. How is forecasting applied in e-commerce? E-commerce companies forecast product demand, website traffic, and recommendation trends. Forecasts guide inventory, pricing strategies, and ad spend optimization. Techniques range from ARIMA for single products to transformers for large-scale multi-product forecasting. What is TimeGPT? TimeGPT is a foundation model for time series forecasting, developed by Nixla. Like GPT for language, it's pre-trained on vast amounts of diverse time series data and can perform zero-shot or few-shot forecasting without task-specific training, making forecasting scalable and accessible. How does TimeGPT differ from classical models like ARIMA? ARIMA requires manual parameter tuning, assumes stationarity, and is specific to one dataset. TimeGPT, by contrast, leverages pre-training across domains, adapts to new series with little or no retraining, and captures nonlinear patterns. It's a shift from handcrafted models to general-purpose forecasting models. How does TimeGPT compare to deep learning models like LSTM or Transformer? While LSTMs or transformers are trained on individual datasets, TimeGPT is pre-trained on a massive time series corpus, enabling transfer learning. This allows zero-shot forecasting and robustness across domains. It reduces the need for heavy retraining, unlike traditional DL models. What are the benefits of using foundation models for time series forecasting? Benefits include zero or few-shot forecasting, cross-domain generalization, lower computational costs for end users, scalability across thousands of series. This makes forecasting more democratized, much like GPT models transformed NLP. What is zero-shot forecasting in TimeGPT? Zero-shot forecasting means generating forecasts for unseen series without task-specific retraining. Since TimeGPT has learned general temporal structures, it can generalize directly. This is powerful for small datasets or rapid prototyping. What is few-shot forecasting in TimeGPT? Few-shot forecasting uses a small number of labeled examples from the target series to fine-tune or guide predictions. It balances pre-trained knowledge with domain-specific adaptation, improving accuracy compared to pure zero-shot. What are some real-world use cases of TimeGPT? Applications include retail, forecasting sales for new products with little data; energy, predicting renewable generation under shifting conditions; finance, adapting to new assets with short history; healthcare, forecasting disease outbreaks in low data regions. How does TimeGPT handle multiple seasonalities? TimeGPT leverages its pre-trained architecture to automatically recognize and model multiple overlapping seasonalities, such as daily and yearly cycles. This is a challenge for ARIMA or SARIMA, but more natural for foundation models. How does TimeGPT adapt to non-stationarity? Because of its large-scale training, TimeGPT captures a wide variety of non-stationary patterns. It doesn't require manual differencing like ARIMA. Instead, it generalizes across trends, regime shifts, and seasonality, making it robust in dynamic environments. How does TimeGPT handle exogenous variables? TimeGPT can incorporate exogenous features as additional inputs. For example, weather, holidays, or promotions can be provided as context. This enhances accuracy while preserving the zero/few shot adaptability of the base model. What are the limitations of TimeGPT? Limitations include dependence on pre-trained data quality, potential domain mismatches, biases from training data, high compute requirements for pre-training, limited interpretability compared to classical models. How does TimeGPT compare to Profit? Profit is rule-based, interpretable, and business-friendly, but struggles with nonlinear patterns. TimeGPT, as a foundation model, is more flexible, scalable, and accurate in complex contexts. However, profit remains attractive where transparency and simplicity are critical. How does TimeGPT compare to domain-specific models like DeepAR or NBE-ATS? DeepAR and NBEATS must be trained per domain. TimeGPT skips this heavy training by using pre-trained temporal knowledge. It achieves competitive or superior accuracy while drastically reducing setup time, making it more accessible. What role does transfer learning play in TimeGPT? Transfer learning is central. TimeGPT leverages knowledge from diverse pre-training and transfers it to new tasks. This means small or sparse datasets can benefit from global patterns learned elsewhere, reducing data requirements. How is evaluation different for TimeGPT compared to classical models? For classical models, backtesting is essential per dataset. For TimeGPT, evaluation also measures generalization, how well it adapts to unseen domains. Metrics like zero-shot accuracy and cross-domain robustness are critical alongside MAE or RMSE. What industries stand to gain most from TimeGPT? Industries with many series and little historical data benefit most. Retail, new SKUs. Healthcare, disease outbreaks. Energy, renewables. IoT, sensor networks. TimeGPT removes the need for per-series model tuning, enabling scale. How does TimeGPT support anomaly detection? By forecasting expected distributions, TimeGPT highlights deviations as anomalies. Its pre-trained adaptability means it can detect anomalies even in series with little data, useful for cybersecurity, fraud, or sensor monitoring. What are potential ethical concerns with foundation models in forecasting? Concerns include data bias, over-reliance on black box models, and risks of overgeneralization in critical fields like healthcare or finance. Transparency and monitoring are essential to avoid unintended consequences. How does TimeGPT fit into the future of forecasting pipelines? TimeGPT can act as a base forecaster for many series, replacing manual ARIMA or SARIMA setups. For high-stakes cases, it can be combined with domain-specific fine-tuning or hybrid ensembles, making pipelines faster and more scalable. What is the future of foundation models for time series? The future includes larger pre-trained models, TimeGPT style, multimodal forecasting, combining text, images, and time series, and integration with agentic systems for decision-making. Just as GPTs transformed NLP, foundation models will revolutionize forecasting. What are the biggest open challenges in time series forecasting today? 3 stand out: robust generalization across domains, data scarcity, or shift, non-stationarity, drift, regime changes, and uncertainty you can trust. Even strong models degrade under distribution and shift, long horizons, and sparse data. Practical systems must combine adaptive learning, calibrated probabilistic forecasts, and continual monitoring. Where is research heading for long horizon forecasting? Long horizons amplify error accumulation and regime changes. Current directions include decomposition-aware transformers, like trend or season separation, frequency domain modeling, like Fourier or wavelet blocks, and hierarchical multi-horizon training with curriculum learning. The goal is to keep forecasts stable while preserving seasonal structure far out. How will foundation models, example is TimeGPT-like, evolve? Expect bigger, more diverse pre-training corpora, multimodal conditioning, like text, weather grids, tabular context, and parameter-efficient fine-tuning for on-prem/edge. Tooling will move toward prompt-style interfaces for temporal tasks, plus adapters that align global knowledge with niche domains without retraining from scratch. What's next for probabilistic forecasting and uncertainty? Focus areas, well-calibrated intervals under shift, distributional alignment across horizons, and decision-aware training. Optimize utility or cost, not just MSE. Techniques include quantile or CRPS objectives with conformal prediction, Bayesian deep nets, and post hoc recalibration tied to business KPIs. How will models handle concept drift and online adaptation better? We'll see plug-and-play drift detectors, streaming fine-tunes with replay buffers, and meta-learning that adapts quickly from small updates. Expect mixture of experts that specialize by regime and safety guards that auto-fall back to simpler baselines when confidence drops. What advances are coming in hierarchical and grouped coherence? Research targets probabilistic reconciliation at scale, coherent intervals, not just point sums, cross-axis coherence, product times region times channel, and global models that learn the hierarchy itself. Optimization-based reconciliation will merge with deep generative forecasters for end-to-end coherence. How will interpretability and explainability improve? Roadmap, attribution over time and variables, which lags or covariates drove a spike. Counterfactual forecasting, what if price increased 5%? And causal features integrated into neural forecasters. Methods blend SHAP-style attributions, attention diagnostics, and structural causal models for actionable explanations. What's the future of causal forecasting? Beyond correlations, causal plus temporal models aim to predict effects of interventions, pricing, promos, policies. Expect time-varying treatment effects, invariant causal features across regimes, and hybrid pipelines where causal discovery constrains deep forecasters, improving robustness under policy changes. How will compute and deployment constraints shape research? Two fronts: efficient inference, like pruning, distillation, low-rank adapters for edge or real-time scenarios, and privacy-preserving learning, like federated differential privacy for regulated domains. Tooling will favor lightweight adapters over full retrains and serverless temporal APIs for elastic workloads. What practical best practices will remain timeless amid new tech? No matter how advanced models get, start with strong baselines: seasonal, naive, ETS, ARIMA. Use honest backtesting with rolling windows. Track bias, calibration, and drift in production. Prefer simple, interpretable solutions when stakes are high. Align metrics with business cost. These habits outlast hype and keep forecasting reliable. Thanks for watching. You've just gone through 200 interview questions covering fundamentals, classical methods, machine learning, deep learning, advanced forecasting, evaluation, applications, and next-gen models like TimeGPT. If this helped you, hit like, subscribe, and turn on the bell so you don't miss our next deep dive into AI, generative models, and applied machine learning. Drop your favorite question in the comments. I'd love to hear your thoughts.